developing next-generation research and technology, facilitating connections between AFRL industry and academia, unlocking innovation through a culture of collaboration. This is the AFRL Regional Network Midwest.
We focus on our investigations on structural mechanics, and in particular the instabilities that structures undergo. And we try to leverage nonlinearity and instability to generate functionality with a view of creating complex reconfiguration and property change purely based on geometrical effects. More recently, we have been very interested on the mechanics of dome-shaped shells. So one of the main innovations in architecture came when the Romans discovered and deployed the arch. That allowed them to make buildings with wider spaces and make them higher, because arches are far more structurally efficient. So inspired on that, we started looking at this type of structures, but now we gave them a little bit more of compliance and flexibility, so you can invert them. And then these structures will be able to hold two different shapes. Once you start connecting them to other domes, and when they start interacting, they allow significant shape reconfigurations. What is most interesting about these systems is that the final shape that they achieve depends on the order in which the domes are inverted. So if I start on this side and I start inverting these domes, it starts to tilt to my left. So I started from right to left. If I reset the structure all the way, and I start inverting now from left to right, then it tilts to the right. These order dependence can be utilized to program or access many different stable states of the structure. One of the applications that we have explored is to generate what we call our meta beams, such as this one here, where we have two of these sheets connected together. By pressing on the different domes that we have, we can change the stiffness of this system. So this stiffness could be utilized by putting it inside a thin wing and enabling a torsional mechanism to change the angle of attack of the wing during flight. And then when you need your wing to be again stiff, all the domes will be reset, and then you would eliminate this type of torsional mode. So the nature of the work is going to combine simulations and rapid manufacturing to enable us to find designs that of structures that are composed of domes that display the surface shapes that are needed. The difficulty in doing this is that these systems are highly nonlinear, which make the simulation of the response more difficult. And in particular, it's difficult to do inverse design, where you have a target configuration. Knowing what distribution of domes is needed is hard. So then we will need to combine both simulations using computer methods and manufacturing, rapid prototyping using 3D printing to enable us to find these optimal designs.
I'm Nathan Hertline.
I'm Phil Buskell. We're both from the Air Force Research Lab, and we're the sponsors on this Midwest Hub project, which is a novel combination of material science and mechanical design to address and explore challenges in morphing high-speed vehicles.
We're really excited about the AFRL Midwest Hub model, which encourages a unique teaming between academia, industry, and the lab.
And we've enjoyed the brainstorming and engagement with Professor Andres Arrieta's group, Professor Rodney Trice, as well as Canopy Solutions as part of this project. Looking forward to the outcomes.
In this part of the project, we are leveraging the mechanics of dome pattern sheets, where the individual domes can be inverted to create a change of curvature to design morphing surfaces that are optimal for different flight speeds of our high-speed vehicles. So we leverage the different topology of the domes and their organization to design these morphing surfaces depending on the flight speed. We use an optimization-based design approach, specifically using particle swarm, for finding the specific parameters, the distribution of the domes and their shape to achieve the different morphing surfaces that we are looking for that are optimal for different flight speeds. These would allow us to obtain metastructures based on this design that you see here, with an organization of dome pattern sheets and some reinforcement underneath that will yield the morphing surfaces that are optimal for different flight speeds or for high-speed vehicles.